This is week 6, channel capacity and classical crypto systems. Lecture notes in the information theory. I'm Hikmet Kamberay, a professor at the Faculty of Engineering. An outline of the lecture for today includes channel capacity, examples of the channel capacity, symmetric channels, and crypto systems. First, I'll talk about the channel capacity. By definition, a discrete channel is defined as a system consisting of an input, alphabet chi, and output alphabet epsilon, and the probability transition matrix P of y given x that expresses the probability of observing the output symbol y given that we send the symbol x. A second definition, it is about the memoryless channel. A channel is called memoryless if the probability distribution of the output depends only on the input at that time, and it is conditionally independent of the previous channel inputs or outputs. A graphical representation of the communication channel is shown on the picture below. So you have a message W sent to some encoder. Then the output, it is a symbol xn from the chi to the power n. Then this goes through a channel which has a probability of obtaining the output y given x, p of y given x. Then on the output, we obtain the symbol yn from the epsilon to the power n. Then if we decode this output, then we obtain an estimate of the input message, which is denoted W at. Another definition, it is a channel capacity. By definition, the information channel capacity of a discrete memoryless channel is defined as C equal to the maximum with probability distribution P of x of the mutual information between x and y, where the maximum is taken over all possible input distribution P of x. To note from this definition, operational channel capacity gives the maximum rate in bits per channel of the information sent with low probability of error. Therefore, the information channel capacity equals the operational channel capacity. Here we drop the word information from now on and mention simply channel capacity. Next, we'll talk about some examples of the channel capacity. By definition, a noiseless binary channel is a channel whose binary input it is reproduced exactly at the output. That is, the transmitted bit it is received without error. This is explained graphically on this picture. So if on the input I have x, which can have the value 0 or 1, then whatever it is the value of x, either 0, we obtain on the output y equal to 0, or 1, we obtain on the output 1 without any error. Now, we can use the definition of the channel capacity to calculate that one. C, it is equal to the maximum with probability distribution P of x of the mutual information between x and y. Here, the mutual information, it is calculated based on the definition as the difference between the two entropies, the Shannon entropy of y minus the conditional entropy of y given x. Now, by definition of the Shannon entropy, h of y is equal to minus sum of all y's, p of y log with base 2 of p of y's. Then by definition of the conditional mutual information as minus sum of all x, sum of all y, p of y given x log with base 2 of p of y given x, then we obtain a plus here, where the p of y given x, it is the transition matrix, probability matrix P, which is this one, the first row, it is P of 0 given 0, and P of y equal to 1 given x equal to 0. On the second row, I have P of y equal to 0 given x equal to 1, and P of y equal to 1 given x equal to 1. which based on the our definition of noiseless channel, binary channel, this it is equal to the matrix 1 0 0 1. Then we denote with P of x the probability distribution of x and P of y the probability distribution of y. This would mean that P of x it is equal to P of 0 and P of 1, because x can take two values, 0 and 1. Since we assume it that each of the input has equal probability to occur, then it means that it is 1 over 2, 1 over 2 each. Then P of y will be equal to P of x, which is 1 over 2 vector, times the transition probability matrix 1 0 0 1. Then we get this product, which will give you the vector 1 over 2 1 over 2, and this will give me a probability distribution of y and the variable. Now we can replace everything on the formula for the mutual information, and we obtain first the Shannon entropy for the y and the variable. It is equal to minus 1 over 2 log with base 2 of 1 over 2 plus 1 over 2 log with base 2 of 1 over 2, which is equal to 1 bit. Then for the conditional entropy, h of y given x, we have, based on the formula above, minus P of 0 times P of 0 given 0 log with base 2 of P of 0 given 0 plus P of 1 given 0 times log with base 2 of P of 1 given 0 minus P of 1 times everything P of 0 given 1 log with base 2 of P of 0 given 1 plus P of 1 given 1 log with base 2 of P of 1 given 1. We replace the values, then we get minus 1 over 2, 1 times log with base 2 of 1, which gives you 0, because log of 2 log with base 2 of 1 is equal to 0, plus 0 log with base 2 of 0 is also 0, because we assume that 0 goes faster to 0 than log with base 2 of 0 to infinite. So the first term gives you 0, minus 1 over 2. Also, for the same reason, 0 log with base 2 of 0 is 0, and 1 log with base 2 of 1 is equal to 0. So I have 0 minus 0 gives me all 0. Then we replace the channel capacity. It is equal to h of y minus h of y given x, or it is equal to 1 minus 0, which is 1 bit. So one error-free bit can be transmitted per use of this noiseless binary channel. Now we consider this noisy channel now, but with non-overlapping outputs. By definition, a noisy channel with non-overlapping outputs is a channel that has two possible outputs corresponding to each of the two input values. Although the channel seems to be noisy, it is not. For this one, we'll calculate the channel capacity, and we'll see that they are the same. So graphically, this will be like this. So for every input, let's say x equal to 0, then I have two possible outputs with equal probability, either 1 or 2, with probability 1 over 2, 1 over 2. And if x it is equal to 1, I have also two possible output, 3 or 4 for y, but one now it is with probability 1 over 3, and the other one with probability 2 over 3. Then again, the channel capacity, it is equal to the maximum of mutual information between x and y with probability distribution P of x, or it is the maximum of P of x, h of y minus h of y given x. Now, each of these terms here will give you minus sum of all y's P of y log with base 2 of P of y plus sum of all x, sum of all y, P of x, P of y given x log with base 2 of P of y given x. Now the P of y given x now, it is the transition probability matrix P, but it has these possible values. The row as first row P of 1 given 0, P of 2 given 0, P of 3 given 0, P of 4 given 0, which is P of 1 given 0, it is 1 over 2, P of 2 given 0 is 1 over 2, 3 and 4 y's cannot be taken if x is equal to 0. So we put 0 and 0. On the second row, I have P of 1 given 1, P of 2 given 1, P of 3 given 1, P of 4 given 1. Then P of 1 given 1, and there is 0, because if x equal to 1, y equal to 1 cannot occur. Then also the second, it is 0. Then the third one, P of 3 given 1, it is 1 over 3. P of y equal to 4 given x equal to 1, it is 2 over 3. Then again, P of x, it is the property distribution for x, and P of y property distribution for y. Again, we assume that the input, it is a binary values, but with equal probability, 1 over 2, 1 over 2. Then P of y, it is P of x times P of times transition property matrix P, 1 over 2, 1 over 2, times the transition property matrix. Then always multiply the vector 1 over 2, 1 over 2 with the first column, 1 over 2 and 0. Then I'll give 1 over 2 times 1 over 2 gives you 1 over 4. Then 1 over 2 vector 1 over 2 with a second column. Then I have again 1 over 4, because 1 over 2 times 0 gives you 0. Then 1 over 2, 1 over 2 with 0, 1 over 3, which gives you 1 over 6. And 1 over 2 times 2 over 3 gives 1 over 3. Then I get 1 over 4, 1 over 4, 1 over 6, 1 over 3. Then we calculate the Shannon entropy for y random variable. It is equal to minus 1 over 4 log base 2 of 1 over 4 plus 1 over 4 log base 2 of 1 over 4 plus 1 over 6 log base 2 of 1 over 6 plus 1 over 3 log base 2 of 1 over 3. Then we use the fact that the log of with base 2 of 1 over 4, it is equal to the minus log with base 2 of 4, which is equal to 2. 2 times 1 over 4 here gives you 1 over 2. But also the second one, it is 1 over 2. 1 over 2 plus 1 over 2 gives you 1. Then for the second one, I'll have 1 over 6 log with base 2 of 1 over 6. Log with base 2 of 1 over 6 gives you minus log with base 2 of 6. Log 6 can be seen as 2 times 3. Then log with base 2 of 6, it is log with base 2 of 2, which is 1, plus log with base 2 of 3. Then you get two terms, 1 over 6 log with base 2 of 2, which is 1. 1 over 6 log with base 2 of 3. Then for the last one, we get minus in front, with log with base 2 of 1 over 3 being minus log with base 2 of 3. You get plus 1 over 3 log with base 2 of 3. So I have 1 plus 1 over 6 for the second term. Then the last two terms can add up and gives you 1 over 2 log with base 2 of 3. Then we can calculate the h of y given x. Then it is equal to minus p of 0, p of 1 given 0, log with base 2 of p of 1 given 0, plus p of 2 given 0, log with base 2 of p of 2 given 0, plus p of 3 given 0, log with base 2 of p of 3 given 0, plus p of 4 given 0, log with base 2 of p of 4 given 0, minus p of 1 times p of 1 given 1, log with base 2 of p of 1 given 1, plus p of 2 given 1 plus log with base 2 of p of 2 given 1, plus p of 3 given 1 log with base 2 of p of 3 given 1, plus p of 4 given 1 log with base 2 of p of 4 given 1. Then you get minus 1 over 2, 1 over 2 log with base 2 of 1 over 2, plus 1 over 3 log with base 2 of 1 over 3, minus plus 0 log with base 2 of 0, plus the same 0 log with base 2 of 0. Then for the second row, you get minus 1 over 2, 0 log with base 2 of 0, plus 0 log with base 2 of 0, plus 1 over 3 log with base 2 of 1 over 3, plus 2 over 3 log with base 2 of 2 over 3. Then we can simplify the two last expressions. Then you get 1 over 2 plus 1 over 2, which multiplies 1 over 3 log with base 2 of 3, minus 2 over 3 plus 2 over 3 log with base 2 of 3. Then you get 1 over 6 plus 1 over 2 log with base 2 of 3. Take the difference of the h of y minus h of y given x. Then you get, then it is equal to 1 bit. So it means that 1 bit can be transmitted per use of this channel. And you notice that this is the same value, the same capacity as the noiseless channel. Now consider another practical case. The channel input is either transmitted unchanged at the output with property 1 over 2, or it is transmitted as the next letter with property 1 over 2. So the input is 26 letters, the English alphabet, using every alternative input letter. We can transmit one of 13 letters without error for each transmission. So you could have the noisy typewriter, which is on the what is shown on the left here. So A goes either to A or B with equal probability, 1 over 2. B now goes either to B or to C with property 1 over 2. And C goes either to C or to D. D goes either to D or to E. And so on. E goes either to E or to F. We can continue like this. And the last one, Z, goes just to Z. Right? Now, this one, it is equivalent to this kind of noiseless subset of inputs. A goes either to A to or B with property 1 over 2. C goes either to C or D with property 1 over 2. And so on. E goes either to E or to F. And the last one, Y, goes either to Y or to Z. So we skip Z goes to Z because this is either to Z or to A in this case, all right? Now we can calculate the C. It is equal to the, again, maximum of P of X with P of X of I, mutual information between X and Y, or the H of Y minus H of Y given X with maximum according to the property distribution P of X. Then we obtain the same formula as we wrote before about using the Shannon entropy formula for H of Y and H of Y given X. Then the P of Y given X, which is the following property transition matrix P. This P of first row, P of A, Y equal to A given X equal to A, P of Y equal to B given X equal to A, then P of C or Y equal to C given X equal to A, and so on. P of Y being equal to Y and P given X equal to A, and P of Z given A. And so on. For the second row, you get P of A given C, P of B given C, P of C given C, P of Y given C, P of Z given C, P of A given E, P of B given E, P of C given E, P of Y given E, P of Z given E. And the last row, it is P of A given Y, P of B given Y, P of C given Y, and so on, P of Y given Y, P of Z given Y. Then P of A given A, P of B given A are equal both with property 1 over 2. Then all the rest, it is 0 because X being equal to A does not go to other values, goes only to A or to B. Similarly, for second row, you get 0, 0, 1 over 2, 1 over 2, and so on, 0. And for the last one, we get all zeros, but the last two, 1 over 2, 1 over 2. Then we assume that all the letters A, C, up to Y are with equal probability, since there are 13 letters, because we removed half, then we get each 1 over 13 of probability. Then we get P of Y, which is P of X times P, transition probability matrix, which is the row vector 1 over 13, 1 over 13, with transition probability matrix. Then you get for P of Y 1 over 26, 1 over 26, and so on, 1 over 26, which is equal to P of A, P of B, P of C, and so on, P of Z. So we have a row vector with 26 elements, each with equal property 1 over 26. Then you get H of Y, it is equal to minus 1 over 26 times log with base 2 of 1 over 26, 26 times. Then it is 26 times 1 over 26, which gives you 1. Log with base 2 of 1 over 26 is minus log with base 2 of 26, with minus in front gives you plus. Then you get log with base 2 of 26. Now log with 26 can be seen as 2 times 13. Then log with base 2 of product, it is log with base 2 of 2 plus log with base 2 of 13. Log with base 2 of 2, it is 1, you get 1 plus log with base 2 of 13. Then for H of Y given X, then we have it is equal to minus 1 over 13 times 1 over 2 log with base 2 of 1 over 2 plus 1 over 2 log with base 2 of 1 over 2, and so on. All the others are 0. For the second row, you get minus 1 over 13. Then the first two zeros. Then you have 1 over 2 log with base 2 of 1 over 2 twice. Then all the rest zeros. And you could continue like this. For the last one, it is minus 1 over 13. All the first are zeros, and the last two are both equal 1 over 2 log with base 2 of 1 over 2. Each of these 1 over 2 log with base 2 of 1 over 2 can be seen as minus 1 over 2 log with base 2 of 2. which is equal to minus 1 over 2. Then if you see here, each row, it is as 2 of such a terms, so each will give you minus 1. All right. Then if you sum this one, you'll get minus with minus in front gives you plus, then 1 over 13 for each row. But there are 13 rows, then you get 1 over 13 plus and so on, 1 over 13. 13 times, then you get 13 times 1 over 13, which is equal to 1. Then you get channel capacity, which is equal to the maximum of the mutual information with proper distribution P of x. This h of y minus h of y given x, which is equal to the exactly 1 plus log with base 2 of 13 minus 1 gives you log with base 2 of 13 bits. Now consider the binary symmetric channel. A binary symmetric channel is a channel in which the input symbols are complemented with a probability P. Here, an error occurs when a 0 is received as 1 and vice versa. So this means that, again, graphically, a binary symmetric channel would be represented by an input, which has two possible values, 0 and 1. Then if the input it is x equal to 0, then the output could be either 0 or 1. And this is a binary. So this means that 0 can go to 1 with P probability or to 0 with 1 minus P. Similarly, if x is equal to 1, then this can go to the two possible values of output, either y equal to 0 with P probability or y equal to 1 with 1 minus P probability. Then the channel capacity using the same formula, it is equal to h of y minus h of y given x with maximum according to the proper distribution P of x, or it is equal to the minus sum of all y's, P of y log with base 2 of P of y, plus sum of all x, sum of all y, P of x, P of y given x log with base 2 of P of y given x. Then the transition probability matrix, it is P of 0 first row given 0, P of 1 given 1. 0. Then this is 1 minus P and P based on the graph shown before. Then second row, it is P of 0 given 1, P of 1 given 1, which is P and 1 minus P. Then P of x, it is assumed as two possible values, x equal to 0 and 1 with equal probability, 1 over 2, 1 over 2. Then P of y, it is equal to the P of x times P, 1 over 2, 1 over 2 times 1 minus P, 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 1 minus P. Then you get 1 over 2 times 1 minus P plus 1 over 2 times P. 1 over 2 can be factorized, then you get 1 minus P minus P plus P. Then you get here PP cancels out. Then you get that it is simply a 1 over 2. All right, because 1 minus P plus P, PP cancels out. Similarly, for the second, 1 over 2 times P plus 1 minus P. Again, 1 over 2, then you get 1 over 2, 1 over 2. Then h of y for a random variable with having two possible values with equal probability 1 over 2. We know this problem, it is Shannon entropy, it is 1 bit. Then h of y given x will be equal to the P minus P of 0, P of 0 given 0, log with base 2 of P of 0 given 0 plus 1 of given 0, log with base 2 of P of 1 given 0. For the second row, it is minus P of 1 times P of 0 given 1, log with base 2 of P of 0 given 1, plus P of 1 given 1, log with base 2 of P of 1 given 1. Then this is equal to minus 1 over 2, 1 minus P log with base 2 of 1 minus P plus P log with base 2 of P. Then for the second term, I will have minus 1 over 2, 1 minus P log with base 2 of 1 minus P plus P log with base 2 of P. Now, if you see, both first row and second row have two terms which are equal, but each it is multiplied by half, so they will give me a full term. So it's minus 1 minus P log with base 2 of 1 minus P plus P log with base 2 of P, which is equal to the Shannon entropy with probability distribution P and 1 minus P. So this, we get that the channel capacity, it is equal to maximum of the mutual information with probability distribution P of x equal to h of y minus h of y given x, and it is equal to 1 minus h of p, bits. Now we can have another case of the binary erase channel. Now, in the binary erase channel, there is a p fraction of bits which are erased, and the receiver knows which bits are erased. The binary erase channel has two inputs and three possible outputs. So the inputs are 0 and 1, and the 0 can go either to 0 with proper distribution with property mass function 1 minus p, or it could go to the y equal to e some error with probability p. Similarly, for 1, x equal to 1 can go either to y equal to 1 with 1 minus p probability or error with p probability. Now, for the same reason, the channel capacity, it is equal to the maximum of h of y minus h of y given x with proper distribution p of x, because it is equal to the mutual information. Or it is equal to this, in terms of probability, to these two sums. One, it is the first sum along the y of p of y log with base 2 of p of y with minus in front. And the second sum is double sum along x and y, p of x, p of y given x, log with base 2 of p of y given x. And the probability transition matrix P, it is equal to P of 0 first row given 0, P of E given 0, P of 1 given 0. And the second row, it is P of 0 given 1, P of E given 1, P of 1 given 1. And it is equal to 1 minus P, P first row 0, 0 P, 1 minus P. Then P of x has two possible values, x, 0 and 1. And we assume now not a binary, but we could have assumed, but it is one with pi probability and the other one is 1 minus pi. Then P of y, it is equal to P of x times P. It is equal to pi 1 minus pi times 1 minus P, P 0, 0 P, 1 minus P. Then you multiply pi with 1 minus P and 1 minus pi with 0. Then it gives pi 1 minus P. Then for the second one, you multiply both by P. All right, then you have factorized P, then you get pi minus plus 1 minus pi. Pi cancels out, then you get simply P. Then for the last term, you multiply pi with 0, 0, 1 minus pi, 1 minus P. Then you get the last term. Then the h of y, it is equal to h of, with this probability, 1 minus P pi, P, 1 minus pi, 1 minus pi. Or then this is equal to minus, all right, for this is the minus here, pi, all right, 1 minus pi log with base 2 of pi 1 minus pi plus, then I'll have p log with base 2 of p plus 1 minus pi 1 minus pi, then I have log with base 2 of 1 minus pi times 1 minus pi, all right? So these are the entropy with this kind of probability distribution, all right? This is taken from this one, all right? So you have this this term on here, all right? So it is the proper distribution of y, all right? Then we can now replace each of these terms. Then you have minus pi 1 minus pi log with base 2 of pi plus pi 1 minus pi log with base 2 of 1 minus pi plus pi log with base 2 of pi plus 1 minus pi 1 minus p log with base 2 of 1 minus pi plus 1 minus pi 1 minus p log with base 2 of 1 minus p, all right? And this is equal to minus p log with base 2 of p plus 1 minus p log with base 2 of 1 minus p plus 1 minus p times pi log with base 2 of pi plus 1 minus pi log with base 2 of 1 minus pi. Then the first term gives you the h with proper distribution p plus the second term gives you 1 minus p times the h with proper distribution pi. Right? Then for h of y given x, we have minus p of 0 P of 0 given 0, log with base 2 of P of 0 given 0, plus P of E given 0, log with base 2 of P of E given 0, plus P of 1 given 0, log with base 2 of P of 1 given 0, minus P of 1 times P of 0 given 1, log with base 2 of P of 0 given 1, plus, then we'll have P of 0 E given 1, log with base 2 of P of E given 1, plus P of 1 given 1, log with base 2 of P of 1 given 1. Or it is equal to minus pi, 1 minus P, log with base 2 of 1 minus pi, P, plus P log with base 2 of P, plus 0 log with base 2 of 0, which is equal to 0. Then minus 1 minus pi, log 0 log with base 2 of 0, which is 0, P of log with base 2 of P, plus 1 minus P log with base 2 of 1 minus P. Or it is equal to pi h of pi plus 1 minus pi h of P, which is equal to, if you simplify this one, h of P. Then we get the channel capacity, which is the difference between h of y minus h of y given x. And it is the maximum with proper distribution pi, 1 minus p h of pi. Then you get 1 minus p bits. If I assume that pi is equal to 1 over 2. All right? For pi equal to 1 over 2, h of pi is equal to 1 bit. Then 1 minus p times 1 gives you 1 minus p bits. Now we give the definition of the symmetric channels. For binary symmetric channel, we get the capacity of the channel per transmission as C equal to 1 minus h of p bits. In addition, for the binary array channel, we got the capacity per transmission. It is equal to C 1 minus p bits. Consider a channel with transition matrix given as P of y given x equal to P 0, 1, 0, 3, 0, 6, 0, 6, 0, 1, 0, 3, 0, 3, 0, 6, 0, 1. You could notice here that x varies along the row and y along the column here. You could notice that P of y given x is the property of y. It is received when x is sent. You can see that the rows here are and columns are permutation of the probability distribution 0, 1, 0, 3, 0, 6. For example, the first one column, it is 0, 1, 0, 6, 0, 3. But the second one, it is a permutation of this one. It is 0, 3 first, 0, 1, 0, 6. Similar, the last column is 0, 6, 0, 3, 0, 1. So any permutation of 0, 1, 0, 3, 0, 6. But even if you see along the row, it is 0, 1, 0, 3, 0, 6. Second one, 0, 6, 0, 1, 0, 3, 0, 3, 0, 6, 0, 1. So this kind of channel where the rows and the columns are permutation of a certain probability distribution, let's say 0, 1, in that case 0, 3, 0, 6, because this is a probability distribution, because 0 plus 1, 0 plus 0 plus 3 plus 0 plus 6 gives you 1. So this kind of channels are called symmetric channels. So for a symmetric channel, the capacity of the channel per transmission, it is again C equal to the maximum of the P of x of the mutual information between x and y. Then the mutual information, it is h of y minus h of y given x, or it is equal to the h of y minus sum of all x P of x minus sum of all y's P of y given x log base of P of y given x. This is the definition of the conditional entropy. And this is equal to h of y minus sum of all x P of x. Now, since the P of y given x are P of x's, then the second sum with minus in front gives me the entropy with proper distribution P of x. Then this is equal to h of y minus, now I have the P of x here times h of P of x. Now this sum here, it is entropy, all right? Could be seen as an entropy, all right? With proper distribution sum R, where the R represent the rows of the transition matrix. And this is less equal to, all right, based on what we've discussed before, log with base 2 of the cardinality of epsilon, because h of y, it is less equal to this one, minus h of r. All right. So the equal signs holds if the output probability distribution, it is uniform. We'll discuss this one previous lectures. This can be achieved, for example, if P of x is uniform. In that case, P of y is equal to sum of all x's from chi, P of y given x times P of x. Now, if P of x is uniform, let's say it is 1 over cardinality of the chi set, then this does not depend on x. I can bring it outside the sum. Then I have 1 over cardinality of chi, sum of all x's from chi, p of y given x. Now, sum of all x from chi, p of y given x, since p of y given x is a probability distribution, then if you sum here along this row, then you get, or column, you get a constant c, which is equal to 1. Then you get c over cardinality of chi, or it is equal to 1 over cardinality of y. So in our case, for example, for the matrix, transition matrix that we gave before, 0.1, 0.3, 0.6, then the channel capacity is log with base 2 of 3 minus h or Shannon entropy with this probability distribution, 0, 1, 0, 3, 0, 6. Now, by definition, a channel is called symmetric if the rows of the channel transition probability matrix P of y given x are permutation of each other, and the columns are permutations of each other. Now, a channel is called weakly symmetric if the rows of the channel transition matrix P of y given x are permutations of each other, and all the columns sums, let's say sum of all x P of y given x, are equal. For example, if you see this, consider a channel with transition matrix given as P of y given x equal to P 1 over 3, 1 over 6, 1 over 2, 1 over 3, 1 over 2, 1 over 6. Now you could see now the columns are not permutations of any probability distribution. However, if you see 1 over 3, 1 over 3, here gives you 2 over 3, right? 1 over 6 plus 1 over 2, all right, will give you here, this will give you 3 over 6 plus 1 over 6 gives you 4 over 6. 4 over 6 gives you 2 over 3. Similar 1 over 2 plus 1 over 6 give you 2 over 3. So they are equal. However, if you see the rows now, it is a permutation of 1 over 3, 1 over 6, 1 over 2. All right. So this is a weakly symmetric channel. So the transition matrix is not symmetric in that case. Now, theorem of weakly symmetric channel. For a weakly symmetric channel, the capacity is given as log with base 2 cardinality of y minus h of the row of the transition matrix, which is achieved by a uniform distribution on the input alphabet. That is P of x, it is equal to 1 over cardinality of chi. Now, the properties of the channel capacity for this one, it is that this channel capacity is non-negative, since the mutual information, it is non-negative number. Moreover, C channel capacity it is less equal to log with base 2 of cardinality of chi, since the C by definition, which is the maximum of the mutual information between x and y, it is less equal to the maximum with P of x, h of x, and this is equal to the log with base 2 of cardinality of chi. Moreover, C, it is less equal to the log with base 2 of cardinality of y for the same reason as above, right? So you could see it is channel capacity less equal to the maximum P of x, h of y. Then this is this log with base 2 of cardinality of y, and you get the formula. Now, the fourth, the mutual information between x and y is a continuous function of P of x. And the mutual information is a concave function of P of x for fixed P of y given x, and convex function of P of y given x for fixed P of x. And also this part of the theorem, or this property we have proved before. Now let's see the cryptosystems. First, we introduce some terminology. The alphabet is denoted by the finite set chi with cardinality absolute value of chi. A concatenation of n letters from the alphabet chi is called n-gram, and it is denoted as xn is a sequence of x1, x2, xn. The set of all n-grams from chi is denoted as chi to the power n. A text will be an element from chi star, which is the union of x to the power n for any n greater or equal to 0. A language is a subset of chi star. By definition, x and y are, let's consider x and y two finite alphabets. Then a cryptographic transformation is a bijection mapping E from the chi star to the y star. Right? Now, some other conventional crypto system consider M a message from the text set chi star. All right. Suppose that this is sent by Alice on the figure below. All right. And Alice wants to transmit it in a secrecy to Bob, which is the last one taking the message. Now, M is called the plain text on here. Alice will first transform the plain text into the so-called ciphertext C by using the mapping EK of M. K, it is some key source here, all right? And it is a ciphertext that it is transmitted to Bob. As I said, K, it is the key source. Now, since the mapping EK, it is a bijection mapping, then the inverse, all right? Let's say DK exists, all right? We have, you might have learned this on discrete mathematics or any mathematics course. And this is called decryption, and it is such that dk of C, it is equal to dk of E of K of M. And this, it is equal to M for every M from the chi star and for every K from some key source set. Now, both Alice and Bob must know the choice of the key K if you want to read it, all right? So this is something. Now, from this picture, Eve here, it is some person then wants to read the message passing from Alice to Bob, all right? However, the encryption here, which is using the key source K, all right, it is the intention, it is to secure the channel for the description by not letting Eve have in it, all right? Now, by definition, a symmetric or conventional crypto system, some epsilon, is a set of cryptographic transformations, epsilon, such that epsilon, it is the set of all transformation mapping, EK, such that K, it is some key source from the set K, where the index set K is called the key space, with elements K called also keys. Now, to note on this one, since the same crypto system epsilon will be used for many people, the set of cryptographic transformation epsilon will be known by the crypto analyst, let's say Eve on this case. Now, crypto analysts can do the following. It can be a passive. This means the crypto analyst tries to find M, or even K, the key source, from some C. Right? If K, it is determined, then the other ciphertext can be broken. Right? Now, it could be also inactive. It means that the crypto analyst tries to actively manipulate the data that are being transmitted. For example, by changing them, by transmitting its own ciphertext and retransmitting all ciphertext, etc. All right, so not something can be done. There are three levels of crypto analysis. Crypto ciphertext only attack. Only a piece of ciphertext is known to the crypto analyst, often context of the message. Known plain text attack. A piece of ciphertext with corresponding plain text, it is known. If the system is secure against this kind of attack, then the legitimate receiver does not have to destroy deciphered message. Chosen plain text attack, the crypto analyst can choose any piece of plain text and generate the corresponding cipher text. The public key crypto system have to be secure against the kind of attack. Assume a probability distribution P of keys k equal to k defined the key space k. A sequence of random variables defines the plain text m of u, which is m of 0, m of 1, up to m of u minus 1. The ciphertext is denoted as c on u, where it is the sequence c of 0, c of 1, c of nu minus 1. And so the c of nu, it is equal to the sum mapping according to E with a source key k of message m of u. Since the E of k is a bijective mapping, the plain text is uniquely defined by the key and the ciphertext. Therefore, you could say that the conditional entropy m of u given the key space k value, a random variable, and c of nu, it is equal to 0, right? So this would mean that uncertainty of knowing m of u given the key space k and the ciphertext c of nu, it is equal to 0. This would mean that what you read, it is without any error. Now, it can be shown that the mutual information between message m of u sequence and c of nu, it is greater or equal to the difference between the entropies of m of u and minus h of k random variable. That determines how much of information c of nu leaks about m of u. The uncertainty about the key together with the information that the ciphertext gives about the plain text, it is greater than or equal to the uncertainty about the plain text. This is what this says in other words. Now you could prove this theorem. We start with chain rule for the entropy. So h of k given c of nu, it is equal to h of k given c of nu plus h of m of u given k and c of nu, which is equal to h of m of u joint entropy f m of u and k given c of nu, which is equal to condition entropy of m of u given c of nu plus condition entropy of k given m of u and c of nu, which is greater or equal to the h of m of u given c of nu, because on the second row, the second term, it is non-negative. That indicates that given the ciphertext c of nu and uncertainty about the key k is at the least as great as the uncertainty about the plain text. Therefore, we can write that the condition m of u given ciphertext c of nu, it is less equal to, just rearrange this one, h of k given c of nu, it is less equal to h of k. Then the mutual information becomes between m of u and c of nu becomes h of m of u minus h of m of u given c of nu, and it is greater than the entropy of m of u minus h of k. Another definition, it is a crypto system is called unconditionally secure, or is said to be perfect secrecy if the mutual information between m of u and c of nu, it is equal to 0. That is, the information capacity to transmit per secure channel, it is equal to 0. A corollary of this, it is that a necessary condition for a crypto system to be unconditionally secure is given by this. It is that h of m of u, it is less equal to h of k. Now, this could be proved easy by combining the output of this with the definition that we just give for the mutual information equal to 0. So this corollary is easily proved. Now, example, suppose that we have 2 to the power kts, all with probability p of 1 over 2 to the power k. Then h of k is equal to minus sum of 5 from 1 to 2 to the power k, 1 over 2 to the power k, log with base 2 of 1 over 2 to the power k, which is equal to k bits. So if the message are the outcomes of you, toss in with a fair coin, then for a perfect secrecy is needed that k to be greater or equal to the Shannon entropy of the M of U. Right. So this was the last slide. Now what you should know from this lecture, you should know about the channel capacity. And very important for the exam, it is how to calculate the channel capacity for simple examples provided on this lecture. If you see at the beginning of the lecture. As I given also before, these are the references for this lecture. Thank you, and I'll see you next time.